Welcome to the video podcast series on stoichiometry. This is part 3. We're going to deal specifically with percent yield in this portion. As we do that, we are going to use a limiting reactant stoichiometry problem as the source problem for how we deal with percent yield. And it's always good to review stoichiometric techniques. This is one of the most important parts of chemistry, affects so much. And a good understanding of how to do stoichiometry problems will take you a long way as you advance in the study of chemistry. So, welcome. We'll need to define some terms. When we talk about actual or experimental yield, it's the amount of product measured at the completion of the reaction. This in a problem, like if you see a percent yield problem in a book, the actual yield has to be told to you. In lab, you'll find an actual yield. It's what you do when you do the experiment and measure the amount of product produced at the end. So the actual or experimental yield, and it can be referred to either way, is the amount of product measured at the completion of the reaction. The theoretical yield is the amount of product predicted by stoichiometry calculations. We've done a lot of stoichiometry. When you put the numbers and do your stoichiometric calculation, the amount at the end that you predict is the theoretical yield. Okay, so you have to keep the actual yield and theoretical yield separate in your mind. They're two different things. Let's consider the following reaction. This is called the Haber process. It's the production of ammonia, which is NH3, from atmospheric nitrogen and hydrogen. And so our reaction equation is N2 plus 3H2 yields 2NH3. Now, you may not have seen the double arrow before, but this is what we call an equilibrium reaction, which means that the reaction doesn't go to completion under normal conditions. So that's going to affect our problem. And here is the problem. If we start with 14 grams of nitrogen and 8 grams of hydrogen, we react this in a closed system. We want to determine first the limiting reactant, B, the amount of ammonia produced if the reaction goes to completion, and C, the percent yield if the amount of ammonia obtained is 14.3 grams. Now, you've done limiting reactant problems before, so what I'd like you to do is pause the podcast and solve the problem. And you have an equation to find percent yield. I want you to go ahead and calculate how much theoretically could be produced if it went to completion, and then compare that to the actual yield and calculate the percent yield. So pause the podcast, do the problem. When you're ready to check to see how you've done, resume the podcast, and we'll move on. Welcome back. Let's see how you did. We're going to go ahead and solve the problem. So I put my reaction equation, and I always put my starting amounts in grams above the reactants in the equation. Helps me to keep track of how much I have. My first step is I want to fill out the BCA table, and I hope that your BCA table looks somewhat like mine. I show you the calculations on how to convert from grams of nitrogen to moles of nitrogen, and grams of hydrogen to moles of hydrogen. And that's very important because in a BCA table, only mole amounts are allowed. So the 14 grams of nitrogen times the conversion factor of 1 mole of nitrogen over its 28 gram molar mass gives us 0.5 moles of N2. 8 grams of hydrogen times the conversion factor of 1 mole of hydrogen over its molar mass of 2 grams of hydrogen gives us 4 moles of hydrogen to start. Also in our before line, the amount of ammonia we're starting with is 0. Well, let's see if you found the same limiting reactant that I did. What I do is I take my leftmost reactant, nitrogen, and I use that starting molar amount of nitrogen. I multiply it times the mole ratio of hydrogen over oxygen from the balanced equation to see how much hydrogen I'm required to completely react the N2. So my 0.5 moles of nitrogen times the 3 moles of H2 over 1 mole of N2, the mole ratio, tells me that I need 1.5 moles of hydrogen to completely react the 0.5 moles of nitrogen. Well, I have 4 moles of hydrogen, so I have 2.5 moles more than I need to completely react the N2. So nitrogen, N2, is the limiting reactant. It's going to run out as soon as it's reacted with the 1.5 moles of H2. So I've identified my limiting reactant, it's nitrogen. I use my limiting reactant molar amount to go ahead and calculate the change line, how much the nitrogen is going to change by the hydrogen and the ammonia, or NH3. So I've already found that I'm going to use 1.5 moles of H2. So in the change line, I'll have minus 1.50 moles of H2. I'm going to use all the nitrogen if I assume this goes to completion. So I'm going to use the minus 0.500 moles of nitrogen. And I take my 0.5 moles of nitrogen, multiply it times the mole ratio of 2 moles of ammonia over 1 mole of nitrogen. And in the change line, my ammonia, if this reaction goes to completion, is going to increase from 0 moles present to 1 mole present, 1.00. How'd you do? Once I have my change line, I can then predict what I'm going to have after the reaction's over, again assuming that this reaction is going to completion. So my after amount for nitrogen is 0. 0.5 minus 0.5 is 0. For my hydrogen, 4 moles in the before line minus 1.5 moles that's used up if the reaction goes to completion leaves me with 2.50 moles of hydrogen when this reaction is over. And for the ammonia, I started with 0. I'm assuming this goes to completion, so I add the change line, and I have 1.00 moles of ammonia left over at the end of the reaction. I want to take the amounts at the end of the reaction and convert them to grams so I can make my comparisons. And again, I am going to calculate not only the amount of ammonia produced in grams, but I'm going to calculate the amount of hydrogen left over. And I just get in the habit whenever I do a BCA table to get as much information as possible from it. And it's a good habit to be in. And you do have to be careful in terms of if your testing time is limited, certainly direct yourself toward what the test is asking for. But it's a good habit always, if you have time, to know as much about your reaction system as possible. This is a way of doing it. So my 1 mole of ammonia, NH3, I convert that to grams by multiplying it by the conversion factor with the molar mass of 17 grams of ammonia divided by 1 mole of NH3. And so we have 17.0 grams of ammonia if this reaction goes to completion. For the amount of hydrogen left over, I have 2.50 moles of hydrogen times 2 grams of hydrogen, the molar mass of hydrogen, over 1 mole of hydrogen. So I have 5.00 grams of hydrogen left over. So, assuming that this reaction does go to completion, I have 5 grams of hydrogen, our excess reactant, left over, and our theoretical yield of ammonia. Remember, when you do a stoichiometric calculation, it's always theoretical. Okay? So our theoretical yield of ammonia, NH3, is 17 grams. We're now ready to proceed to the calculation of the percent yield. Let's check your percent yield calculation. Remember, the formula for percent yield is we take the ratio of the actual yield divided by the theoretical yield times 100. Our actual yield of ammonia is 14.3 grams, so we put that on top. We divide it by the theoretical yield, which is 17.0 grams, and multiply that by 100, and we get a percent yield of 84.1%. So, how'd you do? If you struggled with this problem, identify where your struggle was. If you did the stoichiometry right and just say put the theoretical yield on top over the actual, that's an easy fix. If you're still having problems with the stoichiometry, you may want to go back to the previous podcasts and review those, and then come back through this podcast when you're ready. We've come to the end of part 3 of the stoichiometry video podcast series here at Ontario High School. want to leave you with a quote from great author, Holocaust survivor Elie Wiesel. Because I remember, I despair. Because I remember, I have the duty to reject despair. I wish you well.